Hello and welcome to zwitterstat. This is our third video in the series of videos on matrices and determinants. In the previous video, we have already talked about the types of matrices, how do we add two matrices, and how do we subtract two matrices. In this video, we are going to dive deeper into the properties of matrix addition. So let's get started. The first property of matrix addition is commutativity. Commutativity. Now, if you remember from your prior classes, we have studied that addition of two numbers is commutative. Like 2 plus 3, we know is 5. Now, if I add 3 plus 2, I also get 5. So, this property of numbers where the order doesn't matter at all, the order of addition doesn't matter at all, is what we call as commutativity. Now, this property, which is applicable to the addition of numbers, is also applicable to the addition of matrices. Because after all, a matrix is an array of numbers. It's nothing more. It's just an array of numbers. It may be numbers sometimes, it may be complex numbers, it may be real numbers, it may be some kind of functions, right? So, the whole idea that we have studied in our prior classes that addition of two numbers is commutative, it follows here also when we add two matrices, right? So let's try to give a little sort of proof. How do we say that two matrix addition, that addition of two matrices is commutative? So let's say I represent a matrix A whose element is represented by A sub ij, where I represents the ith column and J represents I represents the ith row. Sorry, ith represents the ith row and J represents the jth column. And m cross m is the dimension of the matrix, where m represents the number of rows and n represents the number of columns. Similarly, I have another matrix B whose element is represented by B sub ij, where I represents the ith row, J represents the jth column, and it is also of the order m cross m, because we know that when we add two matrices, their order must be same. Okay, so now let's start our proof. Let's change the marker. So A plus B can be written as Aij. I will not be writing the dimensions again and again. It must be clear from here that I have already written the dimensions, so I will not be writing it again and again. A sub ij plus B sub ij. Right. So I'm adding my two matrices and we can write it like this way. Now, we know when we add two matrices, the addition of matrices happens element by element. What I mean to say is, if I have a matrix 2, 1, 3, 4, and another matrix 1, 0, 1, 1, and I'm adding these two matrices, so what is happening? The 2 is added to 1, the 2 adds with 1, the 1 adds with 0. That is all the elements that occupy common positions. Like this occupies the top leftmost position, and the element that occupies the top leftmost position in the other matrix are added together. And same happens when we subtract two matrices. So 3 plus 1 and 4 plus 1. And what we see here, that the dimensions of both the matrices have to be same. It is a 2 cross 2 matrix, 2 rows, 2 columns. Similarly here we have a 2 cross 2 matrix, 2 rows and 2 columns, right? So we get our result as 3, 1, 4, 5. So the exact same idea will be followed while we are trying to prove this property. So aij plus bij. Now we see that the elements that occupy the same positions in the two matrices are added together. So we can write it like this: aij plus bij. Right. Now what is happening over here? Two numbers are being added, and we know that whenever we add two numbers, the two numbers obey the property of commutativity. So I can write it like this way: bij plus aij, and further I can write it like this: bij plus aij, and which is nothing but matrix B plus A. And there we have proved our first property of matrix addition, that the addition of two matrices A and B is commutative. So the order doesn't matter at all when we add two matrices, right? So moving on to our next property, which is associativity. Associativity. Now, you must be already familiar what associativity is when you have studied the addition of numbers in your previous classes. So let's say we have three numbers, 2 plus 3 plus 4, and we have write it like this way. So the bracket represents the addition of two numbers, and when these two numbers are added, a third number 2 is added to them. So from our rule of BODMAS, we will first evaluate the brackets. So we can write it like this: 3 plus 4 is 7, 2 plus 7 is 9. But there is another way I can write this. Let's say I can write like this: 2 plus 3 plus 4. Similarly, by following BODMAS, I can evaluate the brackets first, and I get 5 plus 4, and this is 9. So what do you see over here? Clubbing any two numbers is giving me the same result, right? And this property of addition that the numbers obey is what we call as associativity, right? We call it as associativity. Now the same property, that we are clubbing two numbers and then add the third numbers, and clubbing any two numbers will give us the same result. In this case we got 9 in both the cases, is also obeyed by matrices. So if I have three matrices A, B, and C, adding A and B first and then adding C is equivalent to adding B and C first, then adding A to them. And this property of matrix addition is what we call as associative associativity of matrix addition. Right? Associativity of matrix addition. So now we will try to prove this property also in the same way we have done the proof for commutativity. It's not a rigorous proof, but it's a proof that gives you idea that it really holds true when we add more than two matrices. So let's say I have three matrices. Matrix A represented this way, and it has an order of m cross n. Matrix B and a matrix C. Right. So we have three matrices, and we will start the proof in similar way. So let's say let me write it, the statement of associativity, that A plus B plus C equals to A plus B plus C. Right. So We start from the left hand side. Now we can write A like this, B like this, and C like this. Right? Now, what is we know that addition of matrices is adding the elements that occupy the same position in the two matrices. Right? So we can write it like this: Bij plus Cij, right? And we can similarly extend this idea that addition of two matrices is nothing but the addition of elements that occupy the same position in the two matrices to adding A to this matrix, the new matrix that we got by adding B and C. So, right. So we got this our new matrix, matrix A added to B and C. Now, let's write it over here. Now, we know that addition of numbers follow associativity. So I can write this thing, that is Aij plus inside brackets Bij plus Cij as Aij plus Bij plus Cij. Now I start doing the things in reverse. What we have done in these three steps, I will do these things in reverse. So I can write it like this. And further, I can write it like this. That is Aij plus Bij plus Cij, and this is equal to A plus B plus C, and hence we have proved our result for associativity. That associativity also holds true for matrix addition. Now we move on to our third property on matrix addition, which is the property of existence of an additive inverse. Just like we know that an additive inverse exists for numbers, similarly we will prove that there is an additive inverse for a particular matrix that we have, that is given to us. Additive inverse. So what do you mean by additive inverse? Now, just we will go into the flashback of the algebra of the number theory that we have already studied in our basic classes. That, let's say I have a number 2, right? I am having a number 2. Excuse black marker. Let's say I have a number 2, and whenever I add the negative of the number of this number to itself, so let's say the negative of this number is -2, and I add -2 to 2 itself, what will I get? So there's a plus in between them, and there's a minus with this 2. I can write it like this, and I get 0. So what is additive inverse? It's the negative of the number that we are given, right? If I'm having 2, the negative of that number is -2, and that's the additive inverse. And it's a number when it is added to the original number. So I have the original number 2, and when I add this number, the negative of it of 2 to the original number, I get 0. So that is an additive inverse, right? Similarly, if I'm having 5, I add negative of 5 to 5, I get 5 minus 5, which is 0. So this negative 5 is my additive inverse, right? This is my additive inverse. Now the same thing also exists for matrices, right? And here I will not show any proof for this. I will just give you the basic idea for this, right? The previously that I showed, that were also not a rigorous proofs for commutativity and associativity. That that the thing we did here previously gave us the idea to think it in a more general way, right? So let's say I have a matrix Aij, not Aij. I will use a 2 by 2 matrix over here to show you the idea. Let's say A11, A12, A21, and A22. So I'm using a square matrix of dimensions 2 cross 2, right? And the subscripts here 1 1 1 2 actually represents the position of that element in the matrix. So 1 1 represents that it occupies the position in the first row and the first column, right? And we are having two rows and two columns, so it's a 2 cross 2 matrix. So when I say, let's say B is A's additive inverse, right? So I say there's a matrix B which is the additive inverse of A. So A plus B, if I follow the same idea that we have studied in numbers, and that matrix addition is nothing but I'm adding two arrays of numbers, uh, and the numbers are getting added in a way, the numbers that occupy the same position in the two matrices are getting uh, added together, right? So if I use the same idea, then the matrix B, if I'm saying it's an additive inverse of A, then then the addition of these A and B must give me a null matrix. What is a null matrix? Represented by a big O, which is nothing but a matrix where each and every element of the matrix is zero, right? Something like this. This is a null matrix, right? So So addition of matrices follow needs that the two matrices must be of the same order. So the additive inverse will also have to be the order of 2 cross 2, and it must satisfy this condition, right? Okay. So let's see what will be the structure of the matrix B. So I'm having matrix B, and let's say I subtract minus A from both the sides. I'm adding negative of A to both the sides. This cancels with this, and B equals to negative of A. It's the same thing that we have studied for for numbers, right? Additive inverse of 5 is minus 5. Additive inverse of 2 is minus 2. Similarly, additive inverse of a matrix A will be minus A, right? So for our case, our matrix is, sorry, a matrix is A11, A12, A21, A22. So it will be something like this. My additive inverse for matrix A will be something like this. And we can think like this way. It is the scalar multiplication of negative 1 with the matrix A. Right? We can think additive inverse like this. So when we say a scalar is being multiplied with a matrix, as we have seen in our previous video, so scalar, when we multiply a scalar with a matrix, the scalar gets multiplied with each and every element of that matrix. So negative 1 gets multiplied with each and every element, and we get something like this. a matrix whose elements are additive inverses of the elements that we have in our original matrix. And so we have clearly carried the idea that we of additive inverse that we have studied in numbers to the matrices, right? So I will not make the video longer, and we will just end over here and try to revise these concepts that what is the property of additions for matrix addition, and go through the previous videos. And in the next video I will come with multiplication of matrices, as well as in the next video we will also talk about properties of multiplication of matrices, right? And in the future videos I will try to cover some of the questions that we have covered for these for the topics that we have covered in our previous videos, so that you just get familiar with these topics, these concepts, right? So till then, bye bye, thank you.